please.
Thank you. I'll just open my slides. Okay, so just pause a second. Okay, thank you for introducing me. So I'm Dr. David Bynum. I work in the specific research group at Swansea University. And so I'll go through some of our facilities here. So first of all, an introduction to who we are and where we are. So we are a research group in the UK, based in South Wales. We're in Swansea, right on the sea. And our ethos as a research group as specific is researching into energy generation materials. We have full-scale pilot manufacturing capabilities, and we're aimed at buildings as power stations as a concept. So energy generation, storage and release within the building. And within the PV team, we obviously focus on the generation of electricity. We have 3 facilities, all in Swansea, one of which is our Pilot Manufacturing Resource Centre, where we have our larger scale coating technology. So on one side of this clean room, we have the sheet-to-sheet coating, where we have screen printing, triple roll mill into curing process, so this near-infrared curing. As we come to the end of the lab, we'll turn around and see our coating line. So this is a 50-meter long coating line, which is 30 centimeters wide, has different coating technologies on there, including flexogravure, screen printing, and multiple curing technologies. And as we working on buildings power stations, we wanted to take those concepts and prove that they can be done. And so we started off by building our active classroom. So this is a video of the building process, where within that building we have energy storage. So we have PV on the roof, we have jet energy storage in our batteries, and then we can release the energy into the building, so the building is off-grid and energy positive. And following on from that, we've actually built a second building next to it, which is the active office. So this is an energy positive office building. Okay, so moving on to our facilities. So within the team on VIPERLAB, we are working on the scale up of perovskite photovoltaics. Within that, we have 2 routes for scaling up: sheet to sheet through the screen printed mesoporous carbon cell, and roll to roll printing and pilot scale facilities for roll to roll printing. Those are what I'll focus on in the presentation today. As if you want to come and work with us, I expect that would be the main focus of what we can offer. But supporting alongside that, we have a lot of technologies for ink formulation and analysis, things like triple roll mills, surface energy measurement, rheological characterization, which all feeds into to making the solutions that work well with the process. And of course, then we have characterization processes, both for the characterization of the coatings and the performance of the devices afterwards. So things like solar simulators to large area, and stability testing and outdoor testing. So our philosophy for scaling up. So we're going from the lab scale rolled spin coating. We scaling up to 2 methods: sheet to sheet on glass-based devices, and roll to roll on our flexible devices. So our sheet to sheet scale up through screen printing is through the mesoporous carbon cell. So this is a cell where we print multiple layers using screen printing. Use high temperature processing in between, and infiltrate the stack with perovskite to complete the device. And on our lab scale devices, we process that through all stages using laser patterning of the FTO. We then use a screen printing process, and we have a small format, so basically A4 size screen printing to put down the titanium and zirconia. Heat that for up to 500 degrees, then apply the carbon, go through with screen printing, go through another heating stage before we manually infiltrate those. But we also have facilities to go up to large-scale module fabrication. So this is a screen printer that can do 1 meter by 1 meter print area. In this case, we're doing a 30 by 30 centimeter module. We screen print the titanium zirconia, and then come back to do the carbon on this printer. We then will anneal them. So we first do a solvent removal in our web heating process, and then we have an inline conveyor fed Henley furnace. So we'll actually batch process these. So we'll send the modules into the furnace, heat them up to 500 degrees, and then importantly cool them down again before taking them out. Further fabrication processes that we can take up to full module scale is the scribing process. We're using a mechanical scribing here to define the P3 scribe. So it's an automated process to bring the blade down and perform that scribing. And the final part then of scaling the mesoporous modules is to use an automated infiltration process. So moving on from the lab scale infiltration, where we just use a pipette to infiltrate into our 1 centimeter square cells, we've got a robotic infiltration system to infiltrate the perovskite into the module design. And then for testing these modules, of course, we have the indoor, the solar simulators indoors, where we can do the standardized one sun testing. But we also have an outdoor testing rig, so we can mount up our modules onto the rig and continually test these modules over a period of time. If you want them to be one sun outdoors, then the time you come to Swansea is important. So we don't reach 1 sun until about April, but we can continue to measure those modules over a large period of time. We have the picanometer attached, so we can constantly correlate the irradiance with the performance of the modules. Okay, so moving on to our roll-to-roll scale-up path. So we have the ability to, take the solution process route from spin coating through sheet-to-sheet coating of using slot die processes to pilot scale roll-to-roll coating. And skipping the spin coating, we would do a lot of our development at sheet-to-sheet scale. So we have 3 slot die coaters. We have a smaller Scylla slot die coater. We have what we call the benchtop coater, and a flat bed slot die coater. And within that, so the foam coater can coat up to 10 centimeters wide by 25 centimeters long. We have a substrate carrier we've modified to have a vacuum table in line. Quite important for being able to get uniform, repeatable films. It has an integrated oven in line, and with that we can do a roll-to-roll simulation. So we can program it to understand what our roll-to-roll line would be like. So we'll then modify the speed that the substrate passes through the dryer to replicate the residence time of the roll-to-roll system. We have an air knife integrated, so we do for our perovskite, we do gas quenching in line. We also have the ability to heat the system, so we can heat the syringe, actually heat the slot die head and the substrate. Maybe more important for OPV, but we have that facility in line. And we have multiple heads, from very small up to the same heads that we use in our roll-to-roll line. So we can prove our coating on the sheet-to-sheet system and know that we can take those same heads onto our roll-to-roll pilot scale production. And it's at this sheet-to-sheet stage that we do a lot of our development of the coatings before we move on to roll-to-roll. And examples of some of the developments we've done in the inks and coatings is that we will use the viscocapillary model to ensure that we can get a good and stable coating regime. So we will measure the solutions, so we can take the density, viscosity, surface tension, all facilities we have available, measure those properties of the solution, and use the viscocapillary model to determine whether our coating will be stable. And the example here is using the viscocapillary model and the stable, unstable boundary. We can modify either the solution formulation, so perhaps by altering, in this case, the amount of IPA in the solution, we'll change the surface tension and viscosity and move the coating into a stable coating window. Or we can modify the process, so we can say increase wet film thickness of our coating, which then moves it into a stable window, and we're able to coat those. Another example of where we use our characterization equipment and analysis equipment to improve our coatings is we have thermogravimetric analysis. Essentially, this is measuring mass loss with temperature, but one of the areas where we've used it is to optimize solvent blends for the drying profile. So in this case, we were moving from a chlorobenzene solvent, which we could use in our fume hoods, but we wouldn't want to use it for a scaled up process. So we were by testing different solvent blends, we could match the drying profile which we got with chlorobenzene, which gave a very good uniform coating of PCBM. And by matching the drying profile, we were able to get an equally as good uniform coating by avoiding drying defects. Another example of characterization equipment we have available, which we can apply to our coating, is the XPS system. So we have a Kratos Axis Super XPS system available. It does do UPS, but what we tend to use it for in relation to coating is for the surface chemical analysis. So it can do a quantitative chemical stoichiometry up to 10 nanometers of surface depth. If you want to check the conversion of a chemical, perhaps tin oxide. In this case, we used a mapping function looking at the amount of lead that would be shown from perovskite as seen through the P dot layer coated on top. And what this allowed us to do is to identify where we might be getting a few defects across a larger area of the coating at lower thickness. We got a more uniform coating at a slightly higher thickness, and this is a higher thickness than would be optimal for spin-coated devices. And then once we got to even thicker, the device performance dropped off. We were getting a very good full coating, so we can't see the lead through in this device, but it wasn't optimum for the device performance. And then just to mention other tools that we have available within specific, which might not be directly in our group, but we have available, is things like electrical measurements, so JV measurement, maximum power point testing, EQE, CV. We have optical characterization, such as UV-Vis, TRPL, photocurrent and PL mapping. And we have imaging systems such as AFM, SEM, and TEM, all available. Okay, so final bit of infrastructure then would be our roll-to-roll scale-up is to our pilot scale coating facility. So this is our Katima Smart Coater. We have multiple heads, so we have blade coating, gravure coating, but principally we use slot die coating. This is set up within our clean room, so it's in a clean room ambient environment, ambient atmosphere, but a humidity controlled environment. We have 100mm coating width, could say infinite coating length, but we typically put 150 meters of substrate in. We have an inline oven, which is 2 ovens, but it's in total 1 meter long. So we can coat it up to 10 meters a minute. We typically coat at 1 meter a minute just to standardize our drying at 1 meter residence time. And with this facility, we have produced full perovskite devices, all slot die coated, roll to roll. So we will, there's one coating head, but we put the substrate in, run through the first layer. So in our full device stack is tin oxide. We'll rewind, then print the perovskite, follow that with PDOT and complete it with a printed carbon electrode to have a fully coated perovskite device coming off at the end. Okay, so to close, I hope I've introduced you to Specific, the research group based in Swansea University. Showing that we have scale-up facilities from lab to pilot scale production. We have options for both mesoporous screen printing structure and planar structure through roll to roll. And we have a fairly comprehensive characterization set, which we can apply very quickly to the roll to roll or the coated films after we produce them. So with that, I will finish and say thank you very much for listening, and I guess open up to any questions. Guess I will stop sharing.
Thank you very much.
Just coming out.
I have a question for Daniel. I will utilize microphone just because I've had access to microphone. Do you have opportunities for outdoor characterization in a chronism condition? I mean, JV characterization of multiple cell modules, even of different technologies at the same time. And also, if you acquire not only the incident power, also spectral characteristic.
We can definitely have multiple modules or multiple devices connected up and measuring simultaneously. I think we have a bank of 10 source meters to connect up. The spectral output, I believe it is just the power, but I don't have the full information on the system. So maybe if you wanted to contact me outside, I could get more information on that for you.
Okay. May I also ask shortly, are you also looking into the tin-based perovskite at Swansea?
Not currently, but it's something we keep on our radar. We are looking at different perovskite formulations, but it's not a focus right now. We've been really focused on getting to fully roll-to-roll printed perovskite, so that we have a working device coming off at the end, and we will then be looking to improve the performance and maybe introducing new technologies into that. But essentially, we have a device structure where we can put in different formulations or different materials.
I see. Thank you. And Valeria, is it the same story